Well, we're going to conclude now by looking back at the infinitude of primes. We already proved that using the ancient Greek method that was popularized by Euclid. But I want to show you yet another way of doing it that was discovered by the great mathematician Euler in the 18th century, because the method uses a beautiful example of chainsawing the giraffe. It's not a combinatorial method now, but we use infinite series. What Euler did was to start with the harmonic series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, which you know diverges. Remember, that blows up to infinity. So we know that that's not a sum that converges to a finite value. And his bold idea was to factor it as if it were a polynomial. And that's not really legal. You can't play with infinity as if it's a number. But Euler didn't care. Euler was able to chainsaw giraffes before the chainsaw was invented. So Euler took the harmonic series, which is equal to, think of it as being equal to infinity, and he tried to factor it. And the way he factored it was he looked at infinite sums, not the harmonic series, but infinite sums of the reciprocals of primes. For example, if we define s sub 2 to be 1 plus 1/2 plus 1 over 2 squared plus 1 over 3 squared and so on, at that infinite sum, and s sub 3 to be the same thing but for the reciprocals of the powers of 3, and s sub 5 to be the sum 1 plus 1/5 plus 1 over 5 squared and so on, dot, dot, dot. If you look at the product S2 times S3 times S5 times S7 times S11 times S13 going through all the primes, what you'll get is a product of infinite series. The first few terms look like this: 1 plus 1/2 plus 1/4 dot, dot, dot times 1 plus 1/3 plus 1/9 plus dot, dot, dot times 1 plus 1/5 plus 1 over 25 dot, dot, dot. Well, if you expand it, just pretend you're in Algebra 1 and you're expanding polynomials, only it's really scary and infinite, but just get started. You'll notice the first few terms are 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6. In other words, it looks like we're getting the harmonic series. Why? Well, if you think about it, for each number n, the term 1 over n will appear in our factorization. For example, suppose we have a giant number like n equals 360. Then 1 over 360 will appear when we multiply the term 1 over 2 to the third times 1 over 3 to the second times 1 over 5, because 360 factors into 2 to the third times 3 to the second times 1 times 5. Every number factors into primes, and so the reciprocals of those appropriate powers of primes will be in those infinite sums, and there'll be only one case of doing that. It's unique because factorization into primes is unique. So for each number, there's a unique factorization into primes, and we'll find them lurking about as reciprocals in those infinite sums. So every 1 over n will appear when we multiply those infinite sums, which is pretty wild. So what does this have to do with the infinitude of primes? Well, if you think about it, each of those infinite sums, like say s sub 7 is 1 plus 1 over 7 plus 1 over 7 squared plus 1 over 7 cubed and so on, that's an infinite geometric series, and we learned earlier how to sum them up. There's a formula for it, which you've probably forgotten. That doesn't matter. The important thing is the value will be finite as long as the common ratio is less than 1, and here it certainly is. The sum will be finite. So each of those s's, s sub 2, s sub 3, s sub 5, s sub 7, and so on, each of them is just a number, a finite number. So what Euler showed is that the harmonic series is equal to a product of these s2 times s3 times s5 times s7, dot, dot, dot. Now, assume to the contrary that there are only finitely many primes. Then there's only finitely many s sub k's in our product. And each of them is finite, so we'll have a finite product of finite numbers, and we'll get a finite result, and then the harmonic series would be finite. But it's not finite. There's our contradiction. The only way out of it is that there have to be infinitely many primes. Absolutely wild, unexpected way. Who would have thought that infinite series could teach you about primes? It turns out that Euler's little trick here led to an entire branch of mathematics called analytic number theory, which is the application of the science of infinite sums, which is calculus essentially, to number theory.